Hello and welcome to the CDB subthread demonstration. In this video, I will provide a short overview of CDB and the key findings from Testbed 13. In 3D dynamic modeling and simulation, instead of using multiple proprietary databases for each simulation system, there is one common database, CDB, to support all of the simulation clients in real time. Having one CDB data store for various simulation clients addresses correlation between the databases, and making changes to the databases can take minutes or hours instead of days, weeks, or months. For example, if a data provider such as NGA wants to modify runtime simulation databases using the latest source data available, they should be able to add a building which wasn't presented on a previous satellite image of a scene, and it will be immediately reflected in all the simulation systems in real time. CDB has true and accurate 3D geospatial terrain data at its core, as well as 3D objects such as buildings with interior and exterior geometries, 3D moving models such as vehicles, and modifiable textures for models. CDB has been used for 3D simulations such as training, rehearsal, and planning purposes. In flight simulation applications, CDB has been used in training over 100,000 pilots and operators per year in various countries. In October 2016, the OGC approved CDB as a standard for 3D modeling and simulation to establish greater interoperability in the use of geospatial data in the 3D dynamic simulation community. CDB defines the core conceptual models, use cases, requirements, and specifications for structuring, modeling, and storing a tile-based multi-resolution and multi-layer geospatial data store, which is required in high-performance 3D modeling and simulation applications. The demo scenario in the CDB subthread include a CDB provider and a CDB consumer. The CDB provider wants to share the CDB dataset with other users without consumers having to download and manually import the data. The CDB consumer wants to be able to access a CDB dataset using standardized OGC web service protocols and wants the ability to convert CDB feature codes and attribute dictionaries to NSG application schema and vice versa. For the subthread, we have two main requirements to start development: a NAS-based profile and a CDB dataset. With these requirements, we aim to solve the following four challenges: read a CDB data store from disk and publish OGC web services to provide access. Develop a client for reading CDB data stores from local disk and from OGC web services. Map CDB feature codes and attributes into NSG application schema. Analyze the performance and integration of the components. The work and experiments that were done in the OGC Testbed 13 CDB subthread are described in the CDB Engineering Report document. These are the current key findings of the CDB subthread. OGC web services can be used to make CDB data available. A feasibility study for extending OGC CDB 1.0 feature codes and attributes reveals that the current version, 1.0, supports only a limited set of feature codes. The OGC CDB 1.0 can be accessed by OGC web services which support an NSG application schema profile in organizing features and attributes and indexing vector features. For OGC CDB 2.0, we have submitted change requests for supporting application schemas and expanding the supported encoding and data formats. Next, we will have a short video from Luciad that will demonstrate the CDB integration with OGC web services.
This video shows the Luciad client accessing CDB content through OGC web services and conversion to the NAS profile. The use of OGC web services enables any supporting client to access CDB content without the need for a CDB decoder. We start by demonstrating this using a web coverage service from the University of Calgary. Through this service, the client can seamlessly access CDB elevation. This includes access to the raw elevation data values, enabling the possibility to perform client-side terrain analysis. In a similar way, we can get CDB imagery using a web map service, also from the University of Calgary, and CDB vector data using a web feature service from Luciad. By definition, CDB data is organized into multiple tiles and levels of detail. In case of vector data, we use separate feature types for all level of detail. This enables clients to easily choose the desired level of detail using common web feature service functionality. Additionally, we demonstrate that 3D CDB data can also be accessed through the Web Feature Service. To support this use case, we rely on standard GML to exchange the location and attributes of the 3D data. The 3D models themselves are made available through a link in the GML feature attributes. Finally, the client shows the conversion of CDB data to NGA's NAS profile. The CDB standard still uses an old categorization of features based on the Feature and Attribute Coding Catalog, or FACC code. An example is EC30 for a tree feature. The client demonstrates this mapping by enabling the user to load and convert a CDB to the NAS profile. The converted feature codes such as EC5 for a tree show up in the resulting CDB folder structure, as you can see here. And they also show up in the attributes of the features fully aligned with CDB's practices.